All right, so we got this baby that's pushing a brick. And just a reminder, things that I know that we kind of know, but still want to toss it out there, that we talk about friction, because this brick is going to have, perhaps some friction come up later on. And I just want to toss this out there for later in the conversation, that coefficient of friction is equal to the ratio of how much force you feel due to friction divided by the normal force. And there will be people that come along and say, we should probably put absolute values around those guys, because the coefficient is just that, it's a positive coefficient. And of course, that's when things slide. And when things don't slide, we talk about the static friction, that friction that keeps things locked in place, or locked from sliding at least, Fs over F normal. And again, if we're being real purists about this, we should have absolute values on those guys as well. Now, for the story that we're going to tell, I just want to put it out there right now that I'm going to let mu k be equal to 0.500. Okay? Notice there's no units there, because if it was a friction force divided by a normal force, the units, the normal the newtons would eliminate. I'm also going to say that we're on Earth, 9.81 meters per second squared, down. And I got to define myself a reference frame. So we got up, down, right, left, and we'll make up be positive, negative, right positive, left negative. And before we approach the baby with the brick, let's just make sure that we have it all hashed out, how these forces are going to behave. Here's our knockdown illustration with no baby involved. But if I think about the applied force, let's call this applied force, then there would be, I'll do it as a dotted line, I would have F applied X, and that's going to be F applied cos theta, the way that this diagram has been drawn with theta relative to the horizontal. And then I'm going to have F applied Y, FAPI, FAPI, sine theta. All right, based on the way this diagram's been drawn. And then, of course, we'd have FG. And, I just brought up the idea of friction, so we could have an Fk working against the drive external force here, and there'd be a normal force. As I draw the normal force, how should it be relative to Fg? Bigger, smaller, or same? Bigger, smaller, or same? Bigger, bigger. Look, these guys here are driving it into the earth, and really in the vertical situation, vertically it's static. It's not going upwards or downwards. It's not a true statics problem because it's going to slide to the right. So I'm going to, roughly to scale, make my normal force bigger, at least than the Fg. Really, it would be enough to counter the Fg and the F applied Y. All right, so I come back over here and I say, first question, because I haven't even stated any questions yet. This is all preamble. Oh, more preamble. Let's give this thing a mass. The mass of the brick, 10.0 kilograms. Nice round value. The applied force, another round value, F applied equals 100.0 newtons. And the angle relative to the horizontal, let's let it be 30.0 degrees. All right, now we're ready to ask a question. The question now is, find the normal force. And of course, that's Y thinking. So I'm going to say, well, F net, this is vertical thinking, F net Y is equal to F normal. You know what, I think that this time I'm going to make the stylistic choice to put my negative signs in as I build my formula. So I got F normal is going up, but force due to gravity is going down. And F applied Y is going down. So I'm going to, as I build the formula this time, I'm going to make that style choice to put the negative signs in right now. I'm also going to recognize that it's not accelerating in the vertical direction. And so I can come up with my nice little equation. 0 is equal to F normal minus Fg minus F applied Y. And if my goal is to get the normal force. I'm actually doing pretty well here. I can take that normal over to the other side, or since the other two are negative, why don't I take them over to the other side? You know, isolate normal anyway. And I get normal all by itself, and I get a positive Fg and a positive F applied y. And then I could expand this out, making it generalized. Because I'm actually getting tired of calculating force due to gravity separately. I'm getting tired of calculating F applied y separately. And this is one of the other reasons why I might want to be more generalized in my approach, is that I don't like doing all these side calculations. I like just making one mega equation that's just going to be like, boom, all one line. Agreed? It's less organization on my side, as long as I can keep track of what all the stuff is that I'm building here. So mass times acceleration to gravity plus, instead of F applied y, I'm just going to say F applied times sine theta. And now actually I'm just ready to start plugging in values. 10 kilograms, 9.81 meters per second squared, plus 100 newtons, sine 30. Actually, the nice thing about this generalized equation kind of approach is that I make less rounding errors because I just put it all in at once, blammo, and it's all done. I do have to make sure that I do my entries correct, and it does leave less wiggle room for part marks if you're a test writer, you know, because I don't have like all the different things calculated separately. So somebody help a fella out. One line of math, boom, what's the answer? Alex, you got it? 148.1. Nice. 148.1 newtons. It looks like we're going to round to 3 sig figs anyway, so approximately 148 newtons. And we could also throw in up if we really wanted to. And of course, based on the preamble at the very top of the page in my top margin, it makes sense that we would probably want to do the next logical thing, find the friction force, the kinetic friction force, I should say. Now for us at this point, we've actually calculated 148.1 as being the unrounded normal force. If I was somebody who was going to be just thrown in at part B, skip part A, just do part B, thank you very much. You would start off like this, and then what we did in part A was find a generalized equation for normal force. And so if I hadn't already done part A, it would make total sense to say mu k times open bracket mag plus F applied times sine theta. And again, I've got a binomial with a monomial out front as a distributive carry through, but I have this nice like classic math form with ugly variables maybe, but it's all ready to be done in one line. Now since we've already done the legwork of part A and we figured out 148.1, we actually know the contents of that binomial, but I'm just saying. So what do we say? 0.5 was the coefficient of kinetic friction. We're saying we already solved that bit there. And what do we get? What's the friction force? I think it starts with a 7, but I don't know the decimals. Yeah?
It's going to be 1.05 meters.
Nice. Like exactly? Beautiful. That's nice. I love when that happens. All right, so we got our FK value. And then, again, the next logical question, or like in this sequence of progression, would be find the net force. And I could say implicitly in the x direction. Now the reason it's implicitly in the x direction is because we kind of have already stated that the net force in the y direction is 0. But find the net force in the x direction. F net x is written as, well, we could write it as force due to kinetic friction. I'm going to throw in an orange negative sign because we know by reference frame it's working against us. And so I'm going to add in my reference frame negative sign now, plus F applied x, because that's the same style I was doing the previous parts of the question in. So I'm going to have consistent style. Again, if I wanted to be a generalized equation writer, the F net expression would look like this. Negative mu k times the binomial mag plus f applied times sine theta, close bracket, plus f applied x would be f applied times cos theta. And I can't think of a cute little trig identity that's going to let me unpack or simplify that sine theta and cosine theta, so I would just leave it like that. It is the same theta though. But in the end, you guys help me out. Try and put it into your calculator. See what you get. Answer should start with a 1. And be no bigger than 20. James, you got it? You nailed it, yeah. 12.55. What were the decimals?
525.
So 12.5525? Okay. Nice. Now, whether we did it from the full generalized approach or if we use some of our previous values, all good. In this case, there wasn't any real rounding there, so it wouldn't have been a risk of losing rounding information. But we could just jump right in at this general jump-off point. Yeah?
For the final FK, how come this final answer is negative and not as
Oh, you're right. Yeah, why isn't the friction force negative? Usually when we talk about friction force, we think about the absolute values of it. But you're right. In this context, it goes left. Yeah. Because you're right. We're taking that as a negative sign in the next question. In the picture, in context, it's definitely left. Yeah. All right. And then one final logical step to this is a part D. So a part D might be find the acceleration of the system. And what I would say is, like in a textbook, parts A, B, and C would be scaffolding questions. Really and truly, you could just jump to part D. And easily in a first-year university program, I just seen part D as the question. And people say, hey, could you please find the acceleration of the system? And what's more, could you please state a generalized equation for the acceleration of this system? And if you had done parts A, B, and C, that would be scaffolding to set you up for this. But if you didn't have the scaffolding, you'd have to figure this out from scratch and figure out how to work to it. So that's kind of why I'm doing the scaffolding, so we can get to that point, okay? So if I was going to do a generalized equation for the acceleration of this system, I'd say F net sys equals mass of the system times the acceleration of the system. That makes total sense. Rearranging this Newton's second law statement, I would say acceleration of the system is equal to F net sys divided by the mass of the system. Now in this case, the mass of the system is just one brick, so not a problem. We've had multi-body problems we've dealt with in the past. I believe that we could take care of this. If this was a train, we could manage it, right? But the F net for the system, we actually just figured out in the previous line. So, like I said, scaffolding, right? Negative mu k times mag plus, and I haven't given myself quite enough space, sine theta plus f applied times cos theta, all divided by m. And notice the m does not cancel out, so you can't drop that out as a term. It's not present in every term across the numerator. And so that really does end up being the generalized equation. Now, since we did scaffold it, we could use that cheater. Having already done all the stuff before, we did figure out this was 12.5525 newtons in the numerator, divided by the mass of the system, 10 kilograms. which I said it was a nice round mass, and it is helpful. We're just moving the decimal place over 1, right? So we get 1.25525 meters per second squared to the right, and we round it off to 3 sig figs, and we say it's 1.26 meters per second squared. Right. And of course, then we can have the therefore statement. Therefore, the acceleration of the system, or the brick, is 1.26 meters per second squared to the right. There you have it. If I wasn't given parts A, B, and C, at this stage, we should be able to just jump straight to D. But it does take like a little bit of like, oh, how am I going to get there? What's the back processing going to be? And so in a nice textbook, they'll give you part A, B, and C. But if they don't, if they just say jump to D, you got to be able to think, how am I going to scaffold this for myself? How am I going to maybe think through the thoughts of A, B, and C to build that generalized equation at the end? Or am I going to chunk it for myself? Am I going to calculate all these things out separately? From my perspective, I like the generalized equation because I make less mistakes, but it does require that you feel confident about your algebra. It does require that you feel confident about your free body diagrams. So I think it really is a matter of confidence. Okay, so I want you to try it. I won't be putting any marks on generalized equations on a test or anything like that, but try it in the homework. See if you can do it, okay?